In this lab video, we're going to take a brief look into constant motion of an object. We will begin by discussing physics principles at play during the rolling of a soccer ball across the floor. From there, we will explain the mechanics of each of these forces and how they interact to yield the results seen in the video. Then we will proceed to use this information to create a computer model of how this should occur under ideal circumstances, and how our model and our experiment will compare. If you look closely, you can see that in this video, the soccer ball rolls across the floor at what appears to be constant velocity. We will see later on whether or not this is the case. We can analyze this video in Tracker. This program serves to track the ball as it moves during the video. Tracker will plot the position of the ball into a chart, which we can then graph. We will revisit this later on in the video. This figure here is a depiction of the forces acting upon the ball in the video, with the exception of velocity. Velocity is not a force, but I included it for the sake of indicating the direction of movement for the ball. The idea behind Newton's second law of motion is that the net force on an object is equal to its mass times its acceleration, or equivalently, its mass times the change in velocity with respect to time. If there is no net force acting upon the ball, then that means either the ball has no mass, the ball is not experiencing any acceleration, or both of those are true. Given that the ball must have mass, then that means there is no acceleration. Thus, the velocity of our ball is constant and not changing. We should take into account all of the variables in this system so nothing is left unaccounted for, and so that we are able to make all of the necessary calculations that will go into our computer-generated model. For the video, a size 5 regulation soccer ball was used. The mass of said ball is on average 0.45 kilograms, so let's mark that down. While we are doing this, let's get the initial position, which is the origin, and the initial time, which is 0. So, what we need now is an initial velocity. We will calculate the initial velocity here. This is done by calculating the change in position with respect to time. And in order to do so, I have chosen pretty much the both first recorded instances of position and time. Now that we have an initial velocity, we have something to work with for the calculations for our model. Now that we have our variables accounted for, we can begin calculating the velocity of the ball over time. And this is achieved through this equation here. It is worth noting that in an ideal system, such as the one our model exists in, the force of friction due to the normal force from the floor and air drag on the ball are assumed to be negligible. As we plug in our values for the variables in the equation, we come to realize that the lack of a net force on the ball prevents any change in velocity. Therefore, at any point in time that we look at, the ball should be traveling at the same velocity as it is at any other point. So now we know that our ball should be traveling at a constant velocity of 1.65 meters per second in the positive x direction. At this point, we now have all of the information needed to create our computer model. In order to generate the model, the process is relatively simple. We simply assign the values we just calculated to each of our variables within the code. First off, we calculated the mass of the ball, which is 0.45 kilograms, which is here. Then, next you set the initial position of the ball, which is centered at the origin, which is otherwise known as the zero vector. Then, we take our initial ball velocity, which we calculated to be 1.65 meters per second. Then, further on in code, we set the F-net vector to be the zero vector because we also calculated that there was no net force on the ball, resulting in it keeping its constant velocity. Then the next line of code you see is the calculation for the ball velocity, which is going to stay constant, seeing as the F-net was 0, so that there would be no change. And ball position is also calculated in much the same way, in that the position of the ball will be calculated based on the change in velocity over time. As we run the program, we can see that the computer-generated model very closely resembles the movement of the ball from our video. The ball begins at the origin, then rolls across the x-axis. The data from the simulation is then exported to a data table, which we will then combine into the same table as the experimental data so that we can compare our results. If we move to our spreadsheet program and graph our two groups of data together, it becomes easy to make a visual comparison of the two. On first glance, we notice that very clearly our computer model overestimates the position of our ball in time. This was to be expected though. The model predicts the movement of a ball in an ideal universe, which ours is not. The model also assumes that the net force on the ball is 0. However, Our experimental plot indicates that as time goes on, our ball is slowing down. What does this mean in the context of our concepts? This means that the ball is experiencing some amount of negative acceleration. As Newton's second law dictates, if there is some acceleration, then there must be some measure of force acting upon the ball. If we recall the figure from earlier, which illustrated the forces acting upon the ball, there was a drag force and a friction force acting upon it. These two both explain the deceleration of the ball. These forces exist in real life and cannot be ignored or simply negated, and are affecting our ball, and they both account for the difference between our predicted ball position and our actual ball position.